Okay, Assalamualaikum and good morning. Okay, the times now is already 11. So we will start to discuss a new topic. The topic about Z source inverter. So this is chapter number 3. Okay. Chapter number 3, right? 3.13. So for this subject, actually we divide our chapter to discuss various types of converters. So the first chapter on chopper, right? So remember the chopper for chapter number 1. So we focus on 2 applications. So the first on street lighting. So that one just a passive load, right? Resistive and inductive load. Oh, sorry, R load only, the purely resistive load. So we can represent the LED or bulb represent by a resistive load, purely resistive load. Then the second application on adjustable DC motor drive. So where the motor, we can categorize the motor as a combination between resistive and inductive load, RL load. So this case, you need to apply the chopper. So of course, you need to calculate appropriate value of duty ratio for PWM, so that it will produce suitable voltage to be applied across the armature voltage of the motor in order to obtain the desired motor speed. Okay. So remember, for first chapter, we focus on chopper. So I provide 2 examples or application. So one for the street lighting and the second one for DC motor. Okay. And for the second topic, just to second topic on space vector modulation. So means for the second and third topic, sorry, the second and third chapter. So this one, these chapters, we focus on inverter, inverter conversion from DC to AC. So for the second chapter, actually we need to improve the performance of the inverter by enhancing the output voltage using space vector modulation strategy, SVM strategy. So this one we can boost the voltage using the control algorithm. We apply the control algorithm without any modification on the without any modification on the topology circuit of the inverter. So we just retain the structure or the configuration of the inverter, the standard inverter. You have the DC voltage, you have 6 IGBTs. So without any modification on the original inverter circuit. But we can boost the voltage by applying the SVM technique, space vector modulation technique. Okay, that one for the chapter number 2. And for chapter number 3, so this case, this chapter we try to boost the voltage, but with extra or modification on the topology circuit. So you can notice after this, where the circuit is different. Because for the Z source, you need to put additional component. So where the component we refer to as the energy storage element, energy storage component. So remember the energy storage are capacitor and inductor. So remember the capacitor, you can store the energy. So mean you charge the voltage. But for the inductor, you can also store the energy, but that one, the inductor store in terms of current. You remember? So the inductor and capacitor, we classify these two components as a energy storage element where we can store the energy. So this is important in order to boost the voltage. So means we can say that for chapter number 2 and 3, so actually we try to improve the power output or the output voltage of the inverter. Chapter 2 using the space vector, the control algorithm. And chapter 3, by modifying the circuit, we put extra component, the energy storage element, inductor and capacitor. Okay, so to discuss this topic, so firstly, you need to you must able to draw the power circuit topology. So from this diagram, you have the power switches, same as the original inverter. For this case, we apply the 6 IGBTs. So of course, the IGBT has its anti-parallel diode. So remember, the diode is used in order to allow the current to flow back to the source. For example, especially when the motor operate in regenerative braking mode. So mean you allow the current to flow to charge the battery. So that is important of using the anti-parallel diode. Okay, the diode have the 2 terminals. For the input, you have the 3 terminals here. For the output, okay, this is the terminal for the output A, B, and C connect to the motor. Okay, so for the Z source, so actually you need to put additional components. So from the DC battery, so you must put here the diode. So this, okay, maybe I can use different color here. Okay, you just add this component. So this is the diode. So make sure the polarity is correct. So mean from the positive terminal, you connect to the anode of the diode. So then in this area, the rectangular area, okay, boleh. Maybe battery tak ada ni kot. Okay, tak apa. So for the impedance network area, so you must insert first the inductor. So this is the inductor. Okay. So then here also the inductor and the capacitor. So from this point, okay. And another capacitor. So this is capacitor number 2. Okay, so then you need to join this point. Okay, so mean we can define this as L1, the inductor number 1, inductor number 2, L2, E1 and C2. Okay. Okay, another important part you need to define properly the voltage of the inductor and capacitor. So remember the inductor and capacitor are the passive element. So mean the direction of the voltage and current must be opposite to each other. It cannot be same. So means since the current of inductor flow from this point to here, so this is the IL1, and for IL2, the current flow through the L2, so this is IL2. So mean you need to define the voltage across L1 and L2 as this one, plus to minus. Because the inductor and capacitor are passive element. It's not the active element. Active element, for example, battery, a transformer. So mean the direction of voltage and current must be same. But for the passive element, the direction, voltage and current must be opposite to each other. So mean L1, you need to define the voltage L1, VL1, plus to minus. So, direction of voltage and current are opposite to each other. And for L2, so since your current flow from right to left, so mean you need to define the voltage L2, the positive must be here. Minus will be here. So this is VL2. Okay, then the current direction for C1 will be like this. C2 going to here. So mean you need to define voltage across capacitors. Plus will be here for C1. Minus will be here, right? So this is VC1. And for C2, here will be plus. This one will be minus, right? VC2. So you need to define the polarity of the voltage and current properly for inductors and capacitors. Okay, so we know that by using the Z source, actually it can one of the advantage it can offer the voltage boost capability. So maybe you can write here the voltage boost capability in conventional inverter. To mean since of the advantage, it can be widely used for renewable energy system. For example, PV system, photovoltaic or fuel cell. So maybe you can write here due to the advantage. Maybe okay, due to its advantage, the Z source is highly or fuel cell. Fuel cells and etc. Okay. So for example, PV, you have PV solar. So maybe the voltage produced from the solar around 18 volt, 18 volt. But in order to inject to the grid, and because the grid require 230 volts, so you need to boost the voltage because the DC voltage produced from the solar panel just 18 volt, below than 20. So you need to enhance or boost the voltage. So that's why the Z source is widely used for renewable energy interface, especially for PV system or fuel cell. Okay, clear? Otherwise, you need to connect the solar panel in series to increase the voltage. So actually, we can connect the solar panel in parallel in order to produce higher current. You connect in parallel, so then you can produce higher current. But you want to increase the voltage, you need to connect all the solar panel in array in series. Okay, so note that. So you need to take note that for the conventional inverter, for example, using the sinusoidal pulse width modulation, SPWM. Sorry. Okay, the output voltage is always less than the input DC voltage. So remember the output voltage we refer to the fundamental component of the AC voltage, V1. So means this case we can, in other words, we can say that your AC voltage component, the fundamental component of the AC voltage V1, where the harmonic component is 1 and is 1, is always less than the input voltage VDC, the input of the inverter VDC. Okay, so means the inverter cannot fully utilize the input DC voltage. So that's why you need to apply maybe control strategy, use, for example, using the space vector or modifying the inverter circuit by putting additional component. For this case, for the Z source, we apply the inductor and capacitor in order to fully utilize the input DC voltage. So for example, for any modulation techniques, so mean here using the sinusoidal, then you can use the 6-step mode. and space vector in chapter 3. So where the fundamental component using the sinusoidal V1, the maximum voltage is, can someone give the answer? V1 maximum, the maximum fundamental component using the SPWM, sinusoidal pulse width. So the maximum is half of VDC, right? Because remember the fundamental you calculate as MI multiplied by VDC divided by 2. So when you set the maximum MI is 1, so the maximum possible voltage can be produced using SPWM is VDC divided by 2. So mean your V1 always less than VDC. So mean you cannot using this technique you cannot fully utilize the input DC voltage. Separuh the maximum yang boleh pergi. Okay. But for the sixth step, so remember V1, the fundamental component using the sixth step. So the maximum is 2 VDC divided by pi. So this is the maximum voltage can be produced using the inverter and conventional inverter. So this is the highest production of voltage. But the drawback by using the sixth step, it produces higher THD component, higher harmonic components. And one thing you cannot adjust the voltage, and the voltage is fixed, and the fundamental is fixed at 2 VDC divided by pi, and you cannot adjust the voltage using the sixth step. So this is the highest voltage can be produced from the inverter using the sixth step mode strategy. And by using SVM, so what is the maximum fundamental component? You have the space vector rotating to form a circular locus in hexagonal shape. So you can increase the voltage until your circle touch to the hexagonal and the side of the hexagonal. So maybe I can show you. Chapter 2, right? Chapter 2 in which section? Here. Is it this one? Oh, ni. Okay, you have a hexagonal, you map the vectors, then all the points, the active vectors, you join the line, then it will form the hexagonal shape. So then the locus, the circular locus, your mean indicate the reference voltage. So mean the maximum voltage you can extend so that the circle touch to the hexagonal. So this case, the radial component is VDC divided by 3. So this is the maximum voltage can be produced using the space vector modulation. Okay, clear? For SPWM, is half VDC. Then you can enhance the voltage using the space vector until your circular locus touch to the side of the hexagonal. So you have 6-sided, right? So mean this is the maximum voltage, VDC divided by Z3. Means here, the maximum voltage can be produced using the SVM is VDC divided by Z3. So this is for the linear modulation. So actually using SVM, you can extend the voltage beyond this value. But this subject will not cover. So mean you need to apply the over-modulation strategy. Over-modulation strategy. So then your fundamental component can be extend beyond then VDC divided by Z3 until to 6 step. 6 step voltage. So where your fundamental is 2 VDC divided by pi. From 0 to VDC divided by Z3, that one for the linear modulation strategy. But even if you want to extend the voltage beyond this value, VDC divided by Z3, so you need to apply the over-modulation strategy. Over-modulation strategy will not cover for this subject. Okay, so we just focus on linear modulation. Okay, clear? So this is actually this discussion just to highlight where your fundamental component cannot increase so that the value equal to the VDC. So mean it cannot fully utilize the DC voltage. So still your fundamental component cannot reach to the VDC by using this technique, sinusoidal, 6-step and SVM. But it is possible if you apply using the Z source inverter. Z source is possible. Okay, so means this is for introduction, right? Introduction. So make sure you know how to sketch the Z source inverter circuit. And very important for your final exam. Then we move to the next section. So actually this section to compare the switching operation using two techniques. So the first using the sinusoidal pulse width modulation. So mean using the standard inverter. And the second one using the Z source. So let's focus on the first technique for the conventional inverter. So for the standard inverter, you have the DC voltage. Of course, you have the 6 IGBTs or MOSFET. So where it has restriction, right? Where the top and bottom switch for any leg cannot be turned on at the same time. So that is the restriction of using the conventional inverter. So you cannot on simultaneously top and bottom switches. So means from this table, actually we can tabulate. You have 8 possibilities. So remember, for this inverter, you have 2 zero vectors plus 6 active vectors. So mean you can put the switching state for the top from 0, 0, 0 until to 1, 1, 1. So from here, you can have 8 possibilities for combination of switching state. So since the restriction of the conventional inverter, top and bottom switches cannot turn on at the same time, so mean the switching operation must be complementary. So then you need to state. So one thing you have to take note that for the switching state, top switch, for example, for the phase A, the switching state is SA1, subscript A1. For the bottom switch, A2. And we don't need to put SA, then the bottom SA bar. And for this topic, chapter 3. So the top, A1. Bottom, A2. And for the phase B, SB1. The bottom must be SB2. Subscript B2. So means you can state completely, sorry, the table for the bottom switch here, SA2. So when your SA1, and for the case switching combination number 1, SA1 is 0 and SA2 must be 1, right? Here will be 1. So this is 1. B2 also 1. SC2 1. And so mean the switching operation must be complementary. When the top is off, the bottom must on. Okay. So this is for the 0 vector because your state for the top is 0, 0, 0 and V0. So mean here it will be V0. And so remember mapping of vector in chapter 2. And for the second configuration number 2, when your SA1 is 0, SB1 0, but SC1 is 1, so mean for the bottom switches, here will be 1, 1, 0. Okay, and then you can completely inilah. So here will be 1, the bottom off, 1. Pandai pun. 1, 0. Then here, when the top is on, the bottom must off. Here also off. For phase C, when the top is off, the bottom switch must on. Okay, this is the 0 vector V7, right? So mean the bottom state, sorry, all the bottom switches must off. Ini just revision. So then you can sketch the simplified circuit for each configuration. Configuration number 1 until to 8. Clear? So mean for the first configuration, 0 vector. All the top switches are off. SA1 off, SB1 off, SC1 off. And the bottom must on. Here for the second configuration, 0, 0, 1. Okay. So mean you can notice from these simplified circuits, the switching operation must be complementary. And complementary to melengkapi. In Malay, melengkapi. So mean when the top is on, the bottom must off. Otherwise, when the bottom on, the top switch must off. Okay. So this is for the conventional inverter. Okay, clear? Conventional inverter. Okay, but for the Z source, ni Z source. This topic. So this is your Z source topology circuit. So remember, you have additional inductor and capacitors. So of course, you must have the diode here. So what is the purpose of using the diode? So we prevent the current to flow back to the DC voltage, DC source. So remember your DC source, because the Z source we apply for the renewable energy system. For example, PV and solar panel. So we no need to charge the solar panel because this is not the battery. So that's why you need to put the diode. So we prevent the current to flow to charge the solar because this is not the battery. So there is a purpose of using the diode. So it means the inverter just allow the current to flow from the DC side to the AC side. No regenerative braking mode for this case. Okay, so this is the topology. So then because we need to discuss the switching operation for the Z source, so you need to completely tabulate this table. So actually, by using the Z source, it can produce. Maybe I can write here. So actually, the advantage is the Z source can produce 7 additional switching state. Okay, for the conventional inverter, you have 8 possibility, right? By using the Z source, you have extra 8 plus 7. So mean you get how many? 15 switching states, or 15 combination of switching state. So mean here, so that's why you have extra table here. So mean you have additional 7 additional switching state. So mean here, actually you have here, maybe we start from 1, 0, 0. Then I just put first for the top switching state. Top switching state. Remember, for the first 3 column, the switching state for top switches. So mean SA1, SB1, SC1. So maybe I can write here SA1, SB1, and SC1. So this is for top switches. Switching state for top switches. So mean here 1, 0, 0. Then you will have 0, 1, 0, 0, 0, 1, 1, 1, 0. Sorry. 1, 0, 1, 0, 1, 1. Finally, 1, 1, 1. Okay. Okay. So mean here, maybe I use orange color. So for the rest columns of the table here will be switching state for the bottom switches. So here SA1, here will be SA2. The bottom switching state for phase A. It's phase A. So this is for phase B. The bottom switch for the phase B, SB2. The bottom switch for the phase C. Okay. So for the configuration number 9, where the top switching state is 100, SA2, we put, okay, so mean here we can put here all are 1. We turn on all the bottom switches. For the Z source, it allow top and bottom switches can be turned on at the same time. Because of what? Because you have the impedance network in between the DC voltage and the inverter. So mean that it will not produce the short circuit condition because you have the impedance. Right? You have the impedance here. So let's say you put this one VDC is 100 volt, 1000 volt. If you short all the switches and top and bottom turn on at the same time, so actually it will not create the short circuit because you have the impedance in between the DC voltage and the inverter. So that's why for the Z source, it allow the current. Sorry, it allow top and bottom switches turn on at the same time. But for the conventional inverter, this one cannot, because you connect the battery, the DC source direct to the inverter. If you turn on top and bottom switches at the same time, so it will create the short circuit, very high current, then it will damage the IGBTs. Okay, agree? So this is the conventional. Conventional cannot. So that is the restriction of the conventional inverter. Top and bottom cannot turn on at the same time for any leg. But for the Z source, so this one, the inverter allow the current, both switches to turn on, top and bottom switches for any leg or all legs. All legs can, both switches can turn on at the same time because you have the impedance. And your battery, your DC source is not connect directly to the inverter because you have the impedance network, the inductor and capacitor. So it will not create short circuit condition. Agree? Right? So it means you have 7 additional. So you can state all the bottom switching state. And for the bottom power switches, all switches are on. I put the orange color 1 1 1 1. Okay. So from here, so actually you can categorize into 3 cases or 3 groups. So the first, so maybe you can notice here for the first 3 rows mean configuration 9 until 11. Ini saya buat So for the first 3 rows, from here actually you can notice top and bottom switches are on for one leg. Is it right? Only one leg, top and bottom switches are on. So maybe I can state here before that, I forgot to define the definition of the shoot-through state. So actually here, for the Z source, top and bottom switches in a same leg, can be turned on or can be switched on, can be turned on, capital letter on, simultaneously. Simultaneously mean at the same time lah. Simultaneously. Okay. So mean this case, when you face this incident where top and bottom switches are on, so we can define this situation or incident as a shoot-through state. Shoot-through state. Maybe I use here different color. Shoot-through. Shoot dash through. Shoot-through state. So mean top and bottom are turned on for any leg. So mean here we can define this incident as a shoot-through state. So where by looking or analyzing for the first 3 rows, configuration 9 to 11. So you can notice that top and bottom switches are on in one leg. For example, for configuration number 9, so you can notice top and bottom switches are on in leg 1, in phase A, in leg 1 or phase A. Betul eh? So I mean here, you can notice here, SA1 is turned on and S2 on. The other legs, leg number 2 and leg number 3, the switching operation is complementary, right? For example, phase B. Phase B, SB1 is 0. So mean the top switch is off. SB2, 1. The bottom switch is on. Complement kan? And phase C also complement. Top switch for phase C is off. Bottom switch for phase C is on. Complement, right? But for the phase A, leg number 1, top and bottom switches are on. Okay, let's move for configuration number 10. So this case, which leg the top and bottom switches are on? Phase B, right? Or leg number 2. Because SB1 is 1, SB2 also 1. Other legs, leg A, leg 1 and leg 3, top and bottom switching operation are complementary. Okay, then configuration number 11, C N, where leg number 3, top and bottom switches are turned on at the same time. So maybe we can categorize for the first 3 cases here. Mana nak guna color ni? Top and bottom switches are on in one leg or in one phase. Clear? Then we focus for the next configuration. So maybe I can put this one here, the line. Okay, for the next configuration, configuration number 12 and 13. Okay, you can notice that top and bottom switches are on in 2 legs. 2 legs. Let's say for configuration number 12, phase A, right? Phase A turn on. Maybe I use different color ni. Green color. So this one, phase A and phase B, right? Phase A and phase B, leg number 1 and leg number 2, top and bottom switches are on at the same time. Okay, then configuration number 13. Phase A, right? Phase A, B is complement, but C, both switches are on at the same time. Okay, clear? Configuration 14. A complement, B and C. Okay, B and C. So mean here we can categorize for configuration 12 to 14. Top and bottom switches are on for 2 legs, in 2 legs. 2 legs or 2 phases. Okay. And the last, configuration 15. So this case, all switches are turned on. Okay, all switches are turned on. You have 6 IGBTs, means 6 IGBTs are in conducting mode, are on. So in this case, all switches are on. All switches are on. For the ZXOL, it allows the top and bottom can be turned on or switch on at the same time because you have the impedance network in between the DC source and the inverter. Okay, any question? Sekejap ini kelas ni. So now we have in page number 3, right? So actually you have 8 pages, 8 pages. Page number 3. Okay, so by using the Z source, actually you can have extra switching states. So I mean you have 7 additional states. Okay, so we can classify the switching state into 3. So one, when the both switches in a leg, sorry, only one leg, where the top and bottom can be turned on at the same time. And the second category is top and bottom switches are on in 2 legs. And the third category, all switches are on. Okay. So then we move to the next section. So this is a very important section. So actually for this section, we need to do some derivation in order to verify. Maybe I write here. We need to analyze the inverter circuit, the Z source inverter circuit, to verify. So actually this section is to verify the voltage boost capability. The voltage boost capability. So you need to derive some equation. So this case, we start to draw 2 equivalent circuits for 2 cases. So we can divide into 2 cases. Case number 1, for the case of non-shoot-through mode. Non-shoot-through mode means the switching operation is complementary. And when the top is on, the bottom must off. Otherwise, when the bottom is on, the top must off. So this one we categorize as a non-shoot-through mode. Non-shoot-through. And the other case, shoot-through mode. So mean here, top and bottom switches are on at the same time. Because this subject, we focus on the simple carrier base. So we just consider the shoot-through case for the case of all switches are on. All switches are on. Okay, clear? Means 6 IGBTs are in conducting mode. Okay, so mean we define this case as a shoot-through mode. Shoot-through mode. So mean from the original circuit here, so you need to know how to sketch the equivalent circuit for 2 cases. Okay, bye. Okay, case number 1, non-shoot-through. So for the non-shoot-through, so actually the diode is in forward bias. So you just short between these 2 terminals. So mean your diode is in forward bias. And for the case of non-shoot-through, so means your energy storage element, inductor and capacitor, it will store the energy because both element in inductor and capacitor are in charging mode. Because the diode is the diode is turned on, forward bias. So mean you get energy directly from the DC source, solar panel. Okay, for the non-shoot-through, the inductor and capacitor are in charging mode. So mean you get the energy directly from the DC source, PV system, solar panel. So diode is turned on. Then at the output side of the impedance network, so remember you have these 2 terminals. We can define this terminal as a V inverter, the inverter voltage. The input of the inverter voltage, V inverter, V sub INV. Between these 2 terminals, plus to minus. So mean for the case number 1, non-shoot-through mode, so we can represent the voltage across plus to minus terminal as a current source. Because after that you need to assume we put very large value of inductor. So mean it will produce constant current, constant inductor current. So that's why you can represent as current source, between plus to minus terminal, the input terminal of the inverter. Because we put very large value of inductor, then it will produce constant current, constant inductor current, sorry. So that's why you can represent the current source here. So this is for the first case, non-shoot-through mode. So of course you need to define here these two terminal as a V inverter. Okay, so this is for the first case, non-shoot-through. The switching operation is complementary for any leg. Clear? Then we move for the second case. Second case. Okay, this case for the shoot-through mode, the diode is in reverse bias. So mean diode act as an open circuit. By open circuit, diode is in reverse bias. So you open the circuit, and at the input terminal of the inverter between these two terminal. So where since shoot-through mode for any leg, top and bottom switches are on, right? But our case for this topic, we consider all switches are turned on. So mean the voltage across these two terminal will be shortened. Short. Shoot through, shoot through. Top and bottom switches are on. All switches are on. So mean these two terminal will be short. So mean your V inverter will be what? How many volt? Short circuit. 0 volt. Okay, for the second case, the diode is in reverse bias and the voltage across this terminal will be 0. Short circuit. Because top and bottom switches are on. Okay. Okay, so make sure you know how to sketch these two equivalent circuits for two cases, non-shoot-through mode and shoot-through mode. Shoot-through punya situation kan. So this inverter, they allow the top and bottom switches can be turned on at the same time. Okay, so in order to simplify the analysis, because after that we need to derive some equation. So in order to simplify the analysis, so you need to apply some assumption. And the following assumption are met. So the first assumption, you need to assume that the inductance values are same. So mean L1 and L2 are equal. And so mean L1 equal to L2. So mean you can set the value of inductance as L. Because L1, L2 same values. Okay. So then capacitor also same. C1 and C2 also same. So then we can set as C. Then the third assumption, you need to assume that the current inductor is large and constant. So that's why we can represent for the case of non-shoot-through as a current source. Because we consider the current is constant. Okay. So mean the inductor current is assumed to be large and constant. And the switching period is TS, T subscript S. So where the TS is the summation between the shoot-through time, TCH, and non-shoot-through time, T subscript NSH. Okay. So mean where we can define TCH is what? Sorry. Is the shoot-through period. Is the shoot-through period. And T sub NSH is the non shoot-through period. Okay. Okay, due to the symmetrical impedance, because your value of L1 and L2 are same, C1 also C2, so mean we can consider the impedance is symmetry. Then the following relation hold true. So means the capacitor voltage VC1 will be equal to VC2. Then we can set the capacitor voltage as VC, constant value. So that's why I write in capital letter, VC. So same goes for the inductor voltage. Because L1 and L2 are same, so mean the voltage across both inductor, VL1 will be equal to VL2. So mean we can set as VL. Okay, clear? Senang ini. So maybe we just have two classes, two class today and maybe tomorrow. Tomorrow we can extend this topic, so then we complete for this chapter for the Z source. Okay, today we try to complete for 8 pages ni. So then for tomorrow, so maybe we can conduct for the first at the beginning we do the lecture session to complete this topic. Then after that we can proceed to do tutorial. I provide a very simple question tutorial. Then I can demonstrate through the simulation. Just 1 week. Today and tomorrow, then we complete this chapter. Then we have only one chapter rectifier. So then after that we can focus, do the practical session, do your assignment. So maybe if time permit, after this I can explain the assignment after this. This is page number what? 4. Okay. Boleh proceed Can we proceed? Proceed Then here make sure this you can able to scan the equivalent circuit for 2 cases here. Then you have to apply this assumption to simplify the analysis. Okay, Okay, then after this we need to derive some equation. So for the non-shoot through, so remember your diode is in forward bias. Then you can represent the voltage across these two terminal, the voltage across input terminal of the inverter as the current source. So we define this one as a V inverter. Okay, I just redraw. Okay, so you need to obtain the equation of the voltage drop of the inductor for the case of non-shoot through. So that's why you need to put inductor voltage NSH, non-shoot through inductor voltage. So how to calculate? How to obtain the equation? So you need to apply the Kirchhoff voltage law. Macam mana? VL NSH or VL. So remember we have we need to apply the assumption kan, the VL1 and VL2 are same. So then we can set as VL. So non-shoot through inductor voltage as VL. So where VL you can obtain as what? Applying the Kirchhoff voltage law to this network, circuit network. The inductor voltage is the difference between VDC and capacitor voltage. So this is equation number 1. Macam mana dapat? How to obtain this? So you can macam mana? Analyze which loop. You have inductor voltage, VDC and VC. Maybe this loop, right? Here. Is it right? VDC is positive, VL is negative because opposite direction. Then you have VC, opposite direction. By summing all the drop voltage for each element in this loop, you summing, then you total summation must be 0. Then you rearrange, then you can solve for inductor voltage. Is it right? Try. Applying the KVL, Kirchhoff voltage law. Okay, then for V inverter, how to obtain the equation of V inverter? V inverter actually is the difference between capacitor voltage and VL. So maybe which loop? Maybe I use here. Okay lah, orange, okay. VC and VL, VC and VL. Which loop? V inverter here, right? Then you have VC and VL. So maybe this loop, right? Enclosed loop. The dotted line. This loop. Okay, clear? Or you can, sorry, maybe this one I use. Okay. Or V inverter, you can calculate or obtain the equation as 2VC minus VDC. So this is equation number 2. Mana loop? Which loop? You need to analyze. 2VC. Untuk first equation, you have the one inductor and one capacitor. But for the second equation, apa color ni? Color apa ni? Purple color, 2VC and VDC. So you need to sketch, analyze the loop which consists of 2 capacitor, right? And 1 DC voltage. So means here, macam mana buat ni? VC, where is VC? So maybe you go here, right? Then go to C1, this loop. Then you have VDC, right? Then here you have flyover ni. Go to C2, then complete to V inverter. Is it right? Second loop, the purple color equation. So you have this loop, you have 2 capacitor and DC source. So then you get second equation for the V inverter. Okay, this is for the case number 1. None shoot through. Okay. Okay, then we move for the second case. Case number 2, shoot through period. So this case, for shoot through, your diode will be in reverse bias, open circuit. So since shoot through incident, so meaning that top and bottom switches are on. So the voltage across these two terminals is short. So your V inverter is 0 volt. Okay, then same thing kan? Same ni lah story. So you need to calculate the inductor voltage and V inverters. But for this case is shoot through cases and shoot through case, sorry. Okay, so here for the inductor voltage, macam dapat? So actually your ni, so your inductor voltage you can write in capital letter VL. So where your VL is equal to VC. And so which loop you need to analyze? VL and VC. Ni green color, this one. So maybe I use ni VL. The V inverter, right? V inverter is short and VC. So this loop only consists of inductor and one capacitor. Clear? So you analyzing this loop, applying the Kirchhoff voltage law, then you can solve for inductor voltage for the case of shoot through period. So where your VL is equal to VC. For V inverter you just 0 volt. Sorry. So here the value is 0 volt. So this is equation number 3 and 4. Simple. Okay, so for the second case, so you can notice equation number 3, it doesn't have VDC term because you completely disconnect the DC source and the impedance network because your diode is in reverse bias. But for the first case, so you can, these two equation has the VDC term, because the diode is in forward bias. Okay, then you get these 4 equation. Okay, so you need to take note that the average voltage across the inductor over one switching period should be 0. So remember this assumption you need you have to apply when you study for the chopper buck boost converter. The inductor voltage, the average inductor voltage for one switching period must be 0. So same goes for the Z source. Okay, so this case, hence the volt second. So mean you have the inductor voltage multiplied by sampling period, switching period TS. So mean volt second principle. So where you can get this relation, VLTS, you multiply the inductor voltage when for the case of shoot through one. So you must multiply by its time. So this is shoot through time because you get the inductor voltage during shoot through. So that you need to multiply by its period. Refer to the shoot through period. Okay. So this is for the first term is for the case of the shoot through. Then summing with the inductor voltage, but this case during non-shoot through. And non-shoot through, then you need to multiply by its time period. Sorry, by its period. So this time is T non-shoot through. Okay, because you have two cases, kan? During shoot through and non-shoot through. Okay, so this you must equate with the 0 because the average inductor voltage over one switching period should be 0. Okay. Okay, then from here you can simplify this equation. Sorry, maybe this one I write VLVC. Okay, so mean here will be, okay, for VL, the inductor voltage during shoot through. So when you refer from the equation above, so actually VL is VC, right? This one. During shoot through. So mean your VL is VC. So here will be VC, right? During shoot through. So you refer from equation number 3. So this is during shoot through. VL shoot through equal to VC. Okay. So mean you substitute using equation 3 to equation above here, then you get VLSH as VC. Then multiply by its period, shoot through, plus. Okay, for the case of non-shoot through, VLNSH. So you refer equation what? Equation number 1. Okay, equation number 1, because this case non-shoot through. So VLNSH, this one, VLNSH. So I mean here will be using equation 1 is the difference between VDC and VC. VDC and VC multiplied by its period, non-shoot through. Okay, so this we set as equation number 5. Okay, clear? So you just substitute based on the equation that we have derived above ni. Okay, tak ada apa pun. Very straightforward. Okay. Okay, then we proceed to get the relation of the ratio between VC and VDC. So actually you can get this relation as maybe I use the orange color here. The period during non-shoot through, you divide by period during non-shoot through and TSH. So this equation we set as equation number 6. How to get this relation? You actually from 5, not just not from 5, so you get what? VC and VC T none shoot through plus, is it right? VDC and VC, the difference between VDC and VC, you multiply by each period. Here is shoot through. Shoot through ke? Sorry, this one is shoot through. Shoot through. This one is non shoot through. Right? From equation number 5. So you must equate with the 0. And the average inductor voltage over one switching period must be 0. Okay? So then you rearrange this equation. So you try to rearrange the equation, then you can get this relation, equation number 6. So maybe I can extend it. VC, T shoot through. 0. You rearrange so that you bring this term to the right hand side, then you get 0. Plus VDC minus VDC. So betul. VC T non shoot through. So here will be positive, right? Okay, minus then. Minus VDC T non shoot through. But then you factorize VC, right? VC you factorize, is it right? T and H. So saya buat VC, saya factorize, saya letak VC keluar. T, VDC, TSH. Sorry, ini salah. TSH, then you factorize for VC, TSH, right? Then you rearrange, then finally you get equation number 6. Okay? VC and VDC, sorry. VC, oh sorry. Mana aku buat ni? Okay, sorry. Ni salah ni. Saya dah tengok. Here will be VDC, right? VDC. Right. VDC, TNCH, VC, TNCH, tolak VC. Here will be VC, sorry. Okay? Clear? Then, sorry. You apply equation 5, you try to rearrange, factorize, kan? Then finally you can get the relation of equation 6. Equation 6. Okay? Apa ni? Equation 6. Then, okay. Boleh? Siap semua? Okay, then we try to obtain the equation of the peak inverter voltage, the peak DC link voltage across the inverter. So we define as V inverter, P. So this case, you need to apply what equation? Using equation 2 and 6. So you apply equation 2 and 6. So V inverter peak inverter voltage is the difference between 2 VC and VDC. So actually, you can obtain this equation from equation number 2. Equation number 2. Equation number 2 during non-shoot through state. So this V inverter actually is the peak of the DC link inverter. Equation number 2. So it happened when non-shoot through state, during non-shoot through state. So here the VDC, then you try to rearrange the equation so that the equation will be 2VC minus VDC. Okay, so actually this term you multiply by VDC divide by VDC. Clear? Same man. This equation same above, right? Same as above. So then by writing this equation, so actually the aim is we need to express the equation above so that the equation will be 2VC divided by VDC minus 1 multiplied by VDC. Okay. Okay. So then from here, you can see here the term of VC and VDC. And VC and VDC. So that objective why we need to rewrite the equation yang green color to be this one, this equation. Okay? Because we try to write the equation so that the equation will be in terms of VC and VDC. So then we can apply equation VC and VDC from ni, equation 6. Nampak? Okay. So VC and VDC, then you apply equation 6 to substitute the highlighter, the yellow highlighter color term. Okay. So mean from here you can write as 2. So then you have right T non shoot through divided by T non shoot through and T shoot through. So you apply equation 6. Okay. Minus 1 multiplied by VDC. So then, so how to simplify this equation? So actually you can try to expand T and shoot through T non shoot through, right? Plus T shoot through divide by the difference between T non shoot through and T shoot through. Then you multiply by VDC. Okay, is it right? Just mathematics only, eh? Topic what? Topic about fraction, kan? Okay, then you can simplify further the equation above so that the equation will be TS divided by T non shoot through and T shoot through multiplied by VDC. Okay. So remember, clear? So remember your shoot through TS kan? Is summation between non shoot through period and shoot through period. Okay. Okay. Sikit lagi. Okay, then next page. So actually I try to rewrite this equation. I put in this page. Tak dengar pula. So here we just rewrite the equation from the previous page. shoot to period. Sama kita tengok ni. Okay, boleh macam ni. Macam masih dayu lah. Okay, so you rewrite the equation from the previous page, then put to this page. Then, actually you can define the bracket term as, tak dengar pula, bracket term as G. Okay, where G actually is the boost factor. Where G is ratio between TS and non-shoot to period and shoot to period. Okay. So where you can also rewrite G equation as 1 divided by 1 minus 2 shoot through period divided by sampling period or switching period. Okay. How to get this equation? So this is just mathematics. So from this equation, so actually you divide all the term in this fraction and numerator and denominator, you divide by TS. So you have TS here, right? That means here T non-shoot through and T shoot through. So all the term in this fraction you divide by TS. Maybe I use different color. This one you divide by TS. You also divide by TS. You also divide by TS. Okay. So then you try to, then you rearrange, simplifying, and then finally you can get this equation. Right. 1 divided by so we know that the non-shoot through is the difference between TS and shoot through time. Right. Here will be TS. Here from here, so actually is the difference between the switching period and shoot through time. Is it right? Betul. The term that I highlight with the yellow color, non-shoot through period, so actually is the difference between switching period and shoot through period. Right. And betul Dia dapat dari sini. So we know that TS is summation between non-shoot through period and shoot through period. So you rearrange the equation ni, purple color ni. So then you get non-shoot through period, where non-shoot through period is the difference between the switching period and shoot through period. Okay. So then finally you can get this equation. And then with we ni. So where G, we can also rewrite G equation as 1 divided by 1 minus 2 delta. Okay, where this G, the G equation, and 1 divided by minus 2 delta is always larger than 1. G. So this is equation number 8. Equation number 8, right? Here will be equation number, sorry, this equation number 7. Sikit lagi. So where you need to take note that, where G, not that, G you can define as a boost factor. So this term play important role in order to boost the voltage in the Z source inverter. Okay, so G is the boost factor. Okay. Clear? So actually from here, one thing you need to where delta from by comparing these two equations. So actually your delta is the ratio between what? Shoot to period and switching period. Okay. So G is a boost factor. Okay, we know that in the conventional inverter. So maybe I write here. Tak ada rehat ini. We know that the output peak AC voltage, so mean the output of the inverter from the inverter or from the conventional inverter, from the conventional inverter using SPWM technique is, so V1 you have the fundamental component, so equal to the modulation index multiplied by VDC divided by 2. This is question number 9. Okay, where MI is the modulation index. Okay. Last page. One more page. So this is the equation for the fundamental component produced from the conventional inverter, using SPWM technique. So mean you just multiply straightforward kan, modulation index and half of VDC. Okay, for the Z source, ni Z source. Okay, next page, Z source. Therefore, dah tulis dah. Therefore, the peak output voltage in the Z source inverter is V1 equal to the modulation index you multiply by VDC or V inverter? V inverter. Because you have peak of inverter voltage, V inverter peak. Okay. So you divide by 2. So now the input inverter is not VDC. So the voltage is V inverter peak because you have the impedance network. You insert between the DC source and the inverter. So where the input inverter now is the V inverter, it's not the VDC. Okay. So where your V inverter, so what is the equation for the V inverter peak? So you have MI, right? So V inverter peak, so you refer to equation what? Equation number 7. Equation number 7, you have term of G here. Right? So where V inverter peak is G multiplied by VDC. So you have G VDC divided by 2. So this is equation number 10. Okay, now for the Z source, you have additional term, which is G. Nampak? Kalau conventional inverter, it doesn't have G. You have MI and half of VDC. VDC divided by 2. Nampak? But for the Z source, you have additional term, which is G. So G refer to the boost factor. So this term will boost the voltage. So actually this term plays important role in order to increase the voltage, to boost the voltage. So remember the G value always higher than 1. The G value always larger than 1. Nampak? Maksudnya this term will increase the voltage. Nampak? Maksud kalau G you set value is 2, so mean dia akan amplify 2 times the voltage produced from the conventional inverter. Conventional inverter, maybe the maximum is half of VDC. When you set MI is 1. But with G, so you can set, and maybe we will set value G to maybe 5 times. So mean your punya production of those voltage from the Z source is 5 times from the conventional inverter using the SPWM technique. And so this is ni lah G. Okay, so maybe we can conclude that, or maybe from here you can to note that, you can to take note that last the output AC peak voltage from the Z source inverter is G. So you know that G is the boost factor. G is the boost factor. G times then the convention, then G times the conventional inverter output. Boleh lah. The conventional inverter output, and the value of G is always in the output. Okay, finish. Pada D. Berapa dah? 12. 12:30. Okay, any question? Ada yang mau tanya? Okay, for today's class, we discuss for the introduction, what is the advantage of using the Z source. Then we try to analyze the circuit by drawing 2 equivalent circuits, and for 2 cases, shoot through and non-shoot through. Then using this equivalent circuit, we derive some equation. Then we actually we need to to verify how the Z source can boost the voltage. So this is the process. So you can you please study lah, make revision to understand how the derivation, how to derive the equation. So finally you can derive where the fundamental obtained produced from the Z source, you have additional G term here. Okay. Yeah. So maybe tomorrow class we start at 8:15. Tomorrow, here DK1. So for the tomorrow's class, I will demonstrate how the Z source can boost the voltage through the simulation. Okay, before we end the class, maybe kejap je. For the assignment, so maybe we can start to, you can start do the assignment. Assignment. So this is the task. Here. Okay, actually this assignment you can download from MTeam. I put already here. Mana MTeam? Where is the MTeam? Okay. How to see the ni? MTeam. This one. Okay, you can go for ni file tabs ni. So I have create the folder, assignment folder. Okay, you can download all the material from here, the task and the file, the simulation file. Okay, this file actually is not a complete version. So you need to completely construct the model using this file. Okay, okay. So actually maybe I can open the file here. Maybe try to open MATLAB. Okay, the task maybe while we wait for the file to be open. So maybe I can explain the task for the assignment. Here. Okay, so actually the assignment. Okay, you can read the objectives. So make sure after you complete perform the assignment, then you able to design and analyze and implement. Implement the space vector modulation. So this is SVM actually using the DSpace R&D controller board for adjustable speed drive. So I mean you can control the motor speed of the induction motor for low, medium, and high speed using the space vector technique. Okay, for the first part, so actually this one we have already discussed from tutorial session. And remember for tutorial last week, we discussed 3 questions. Same pattern of question here. So you have DC voltage, the switching frequency and sampling. So then for a given reference voltage, then you need to calculate the on times, TA, T1, for example, T1, T2, and T0 or T7. And you calculate using appropriate equation, then you need to sketch the switching status waveform, SA, SB, AC. Based on the sector. Maybe sector 1, the switching pattern should be different for the other sector. So then you need to model the space vector using the MATLAB. Then you need to verify the waveform. You compare the calculation and the simulation result. Okay. So then lastly, in part C, you need to implement the hardware design. Then you verify the design through experiment. So mean you need to implement the SVM using the DSpace controller board. Okay. Then you can obtain the result using the oscilloscope. Then you compare the result, the experiment result with the calculation. Okay. So this is for the switching pattern. And part B, part 2. So here is very simple lah. So then you can apply your design, your SVM. Then you run using the DSpace to control the motor speed. So I think this one maybe we can explain in detail when you go to the lab. Maybe for this time you can start construct the simulation model first. After you finish, you get the result okay, then we can proceed for the part 2 for the experiment. This one maybe we can have a special session lah. After we complete all the syllabus, then we can go to the lab for doing the for the part 2. Okay. Clear? Okay, simulation actually here. This is the simulation. Lambat pula buka. So no need design PCB tak ada design PCB. We just do the simulation and run through using the disk space. Only that one. Okay, for this simulation. So maybe you can try to open the file. So actually I have provide to you ni construction of the inverter circuit, the measurement unit here. Okay, so your task is to construct completely these two subsystem. Ni the area that I ni put the area here. So you need to completely construct this model for the SVM modulator. So here, when you double click this block, blank page here, this one. So you need to know the process, how to write the algorithm. Saya tak boleh ni. So maybe I can explain how to use this MATLAB function block. So actually you must have, firstly you need your coding, this is the C code. Firstly you need to initialize the value, the input value, or the value maybe you set 0. Then you need to define the input. What is the input? For example, this case the input is VD and VQ. The D voltage and Q voltage, VD and VQ, your reference voltage. So then next step, you need to detect the sector. Your space vector located in which sector? Sector 1, 2, 3 or 6. So you know this. Then you need to calculate the alpha value, the angle within a sector. Then you need to calculate the V alpha, V beta. Then you calculate the on time based on the equation that we have derived in class. Means you need to calculate TA, TB and T0. Then you calculate the duty ratio. Then finally, the production of the switching state. So actually, maybe I can provide the flow chart, how to write the coding. Maybe next week. Okay. Then here block to generate the switching status. Maybe I can explain detail lah next week. Okay, you try to do first. Maybe you try to do for the calculation first. Part 1. The calculation first. Okay, clear? Alright. Okay, kita end the class. So maybe we have class tomorrow. Tomorrow morning start at 8:15 to discuss the tutorial on the Z source inverter. Okay, thank you. Habis. Ada apa nak tanya? 8 suku. 8:30 lambat. Okay lah, 8:20. Okay. Alright.